Welcome to Lecture 4, Logical Database Design and Relational Model. Let's learn in a little bit more depth how we deal with the relational model, and we will be actually having mathematical equations, and that we will be discussing in this lecture. The objectives are defined terms that we are going to deal with DBMS. List 5 properties of relations. State 2 properties of candidate keys. Define first, second, and third normal form. Describe problems from merging relations and transform entity relationship and enhanced entity relationship diagrams to relations. Create tables and entity and relation integrity constraints. Use normalization to decompose anomalous relations to well-structured relations. Components of relational model: data structure such as tables, rows, and columns. Every table has some rows and columns associated. It's pretty much like Excel sheet, which has rows and columns. However, stores the data which is non-visible until we put a structured query language on top of it. A structured query language comes under data manipulation. The powerful SQL operations for retrieving and modifying data. So CRUD, C is create, R is read or retrieve, U is update, and D is delete. Data integrity comes into play. Mechanisms for implementing business rules that maintain integrity of manipulated data is also very important to learn. A relation is a named two-dimensional table of data, and that means if we have student table, that means we have student's name, which has first name, middle name, last name, then address that has the street number, street address, unit number, which can be apartment, then the city, zip, and county, and the state. This consists of rows, records, and columns, attributes or field, requirements for a table to qualify as a relation. It must have a unique name. Every attribute value must be atomic, not multi-valued, not composite. Every row must be unique. Can't have two rows and exactly the same values for all their fields. That's called redundancy, duplication. Attributes or columns in table must have unique names, like first name, middle name, last name. The order of columns must be relevant. The order of rows must be irrelevant, and note all relations are in the first normal form in this typical discussion that we are looking into at this very moment. Correspondence with entity relationship model. Relations are tables, correspond with entity types and with many-to-many relationship types. Many students are taking many courses. Rows correspond with entity instances and with many-to-many relationship instances. Columns correspond with attributes. Note the word relation in a relational database is not the same as the word relationship in an entity relation model. We will be looking at all of this in a little bit more detail in the coming slides and the coming lectures. People often confuse the term relation with the term relationship. A relation is a table that follows certain rules and refers to actual relational database architecture. A relationship is a conceptual term that refers to how entities relate to each other. The entity relationship concept of relationship will be implemented by primary and foreign keys connecting to the database relations in specific. Keys are to databases as identifiers are to the ER models or entity relationship. Primary keys are unique identifiers of the relation. Examples include employee number, social security number, and the list goes on. The guarantee that all rows are unique. Foreign keys are identifiers that enable a dependent relation on the many side of a relationship to refer to its parent relation on the one side of the relationship. Keys can be simple, a single field, or composite more than one field. Keys are usually used as indexes to speed up the responses to and user queries. So we will look into this with few examples which are going to be coming in the future slides. So the schema for four relations, Pine Valley Furniture Company, as we are discussing, and the enhanced entity relationship notation are customer ID, customer name, customer address, customer city, customer state, and customer postal code. So it's a possibility that if there are 1,000 customers, they might be living in one city and one state. So that repetition is acceptable. However, one customer will have only one customer ID. Order has order ID, order date, and customer ID. So one order would have 10 customers in it. Order line has order ID, product ID, and ordered quantity, and that is coming in through the actual table order. Product has product ID, product description, product finish, product standard price, and product line ID. So the solid underlines indicate the primary key, dash underlines indicate the foreign key. In order line, there is a composite primary key, order ID, and product ID together. Each of these fields are also foreign keys to the other relations order and product. The relation on the many side of 1 to n relationship will have a foreign key that corresponds with the primary key of the relation on the one side. Anytime you have an many to many or m to n relationship between entities, this must be implemented via a separate relation, often called an intersection table or a junction table. The order line table is an example of a relation that implements a many-to-many relationship between orders and products. Each order may involve several products, and likewise each product could be involved in many orders at the same time. So the domain constraints, allowable values for an attribute, includes data types and restrictions on values. And entity integrity is in reality no primary key attribute may be a null. A primary key must contain data values. Referential integrity has rules that maintain consistency between the rows of the two related tables. So I would suggest to you to read the assigned textbook for this chapter. This will allow you to understand more in depth of the book that is mentioned and is given in the first slide. So because some tables are dependent on others, it is important to control how data is to be deleted. Referential integrity rule prevent data from being deleted where there is other data dependent on it. For example, a customer will not be deleted from the database if there are existing orders that were generated by that customer. The delete rules specify how such relations can be controlled within the database. So for example, delete rules apply restrict, cascade, set to null. Restrict is don't allow delete of parent side if related rows exist in the dependent side. Parent can be the customer and order is the dependent. If there is customer, then the order will happen. Cascade is automatically delete dependent side rows that correspond to the parent side rows to be deleted. Set to null, set the foreign key in the dependent side to null if deleting from the parent side not allowed in the weak entities. In the relation diagrams of this chapter, arrows between foreign and primary keys depict referential integrity constraints. So referential integrity is something that we must be working very closely in the database management system. Let's look at referential integrity in a little bit more depth. Referential integrity is a concept in databases that ensures the consistency and accuracy of data by maintaining valid relationships between tables. One example is a simple customer and order database. In this scenario, each order must be linked to a valid customer. This means that you cannot have an order for a customer that does not exist in the customer table. If you try to delete a customer who has placed orders, referential integrity rule would prevent this deletion unless you can also delete or reassign their orders. Another example is a library system with books and authors. Each book is written by an author who exists in the authors table. Referential integrity ensures that you cannot add a book with an author that is not listed in the authors table. Similarly, if you try to delete an author who has written books, the system would restrict this action to maintain data consistency. You would need to handle the books associated with that author first, either by deleting them, reassigning them to another author, or handling them in some other appropriate way. Another example is an academic database with courses and students. Each student is enrolled in courses that exist in the courses table. Referential integrity makes sure that you cannot enroll a student in a course that does not exist. Additionally, if you attempt to delete a course that has students enrolled in it, the system would prevent this to maintain data integrity. You would need to address the enrolled students first, perhaps by unenrolling them or transferring them to another course before you can delete the course. Hopefully this has given you in-depth understanding. So the SQL table definitions. Referential integrity constraints are implemented with foreign key to primary key references. Here we are creating a table, customer T, which has customer ID, customer name, address, city, state, postal code, and all that attributes are the number, varchar or variable character, and variable character with a char or character, and varchar 2. It's technically variable character with a length, double length. Constraint customer PK is primary key customer ID. Whereas create a table order T, and this is a very good example for you to understand how the tables are created with referential integrity associated. You do not need MySQL, SQL Server, Oracle, or DB2 to create these tables. You can create these tables by exactly the same way in a Microsoft Word or a Notepad for your understanding. So this is a very decent example that is given for customer, order, product, and order line tables, as we were discussing in the previous lectures as well. Mapping regular entities to relations. Simple attribute ER attributes map directly onto the relation. Composite attributes use only their simple component attributes. Multi-valued attribute become a separate relation with a foreign key taken from the superior entity. So that is another understanding that I would like to share with you in a little bit more depth. There are 7 slides in continuity to understand these concepts. So example of mapping a regular entity. Customer entity type. Customer has customer ID as a primary key. Customer name, address, and postal code as the other data that is needed for a customer. Whereas customer relation has customer ID, customer name, customer address, and customer postal code, and the data goes underneath the relation. Whereas entity types is given in the A section of the figure, and B section has a relationship, how it goes when we start entering the data in the table in terms of rows. Okay, next is mapping a composite attribute, customer entity type with composite attributes. So customer has customer ID, customer name, address, and the composite attribute is customer street, customer city, customer state, and customer postal code. Whereas the B section, it tells us the customer relation with the address details, so customer ID, and you can see it's pretty much like an Excel sheet where you can start entering the data in it to save and store for the future usage. So employee entity type with a multi-valued attribute, employee ID, employee name, employee address, and the skill. Definitely one employee has way more than one skill. It can be Microsoft Word, it can be Excel, it can be PowerPoint, or it can be anything else, Microsoft Access. Employee and employee skill relations, whereas employee ID, employee name, and employee address, whereas one employee can have 10 skills or 15 skills associated. So the multi-valued attribute in ER models must be converted to a separate relation in the logical database design. This is because there is no such thing as multi-valued attribute in relational databases. Remember the rule for the first normal form. In this case, there is one-to-many relationship. In the final database structure, the employee's skill relation has a composite primary key, that is employee ID and skill. The employee ID portion of this composite primary key is also a foreign key to the employee table. So mapping week entities involves creating a structured representation of the days of the week and their relationships in a database. One example is a simple calendar application. In this scenario, you might have a table for the days of the week, with each day, such as Monday, Tuesday, having its own record. You could also have a table for events, with each event linked to a specific day. This mapping ensures that each event is associated with a valid day of the week, maintaining that integrity of the calendar data. Another example is a school timetable system. Here you might have a table for the days of the week and another table for classes or lessons. Each class is scheduled on a specific day of the week. Mapping these entities involves linking each class to the appropriate day, ensuring that the timetable is accurate and that classes are not scheduled on invalid or non-existent days. This structure allows for easy to find and manage the school schedule. Another example is the fitness center's class schedule. In this case, you might have a table for the days of the week and another table for fitness classes. Each fitness class is offered on a specific day of the week. Mapping these entities involve associating each class with the correct day, ensuring that the class schedule is organized and that classes are not listed on days when they are not offered. This structure helps in managing the fitness center's operation and provides a clear schedule for members. So week entity dependent. Employee is employee ID and employee name. Claims to be a dependent, whereas dependent has a name, first name, middle name, last name, middle initial, last name, date of birth, and gender. Relations resulting from a weak entity is employee ID, employee name. Dependent first name, middle initial, last name, and employee ID and date of birth and gender are pretty much the weak entity relations. So now look at one-to-many, many-to-many, and one-to-one relationship with one example each. Consider a simple blog platform. In this scenario, you have authors and blog posts. Each author can write many blog posts, but each blog post is written by only one author. This is one-to-many relationship. If you have an authors table and posts table, each post in posts table would be linked to a single author in the authors table. This structure allows you to easily query all posts written by a specific author. Whereas many-to-many example could be, think about a movie streaming service. You have movies and actors. Each movie can have many actors and each actor can be in many movies. This is many-to-many relationship. To manage this in database, you might have movies table, an actor table, and a junction table like movie actors that links movies and actors together. This table would have entries for each movie actor pairing, permitting you to track which actors are in which movies. One-to-one. Consider a system for tracking employee information at a company. In this case, you might have a table for employee details like name, department, etc., and another table for employee contact information like email, phone number, or something like that. Each employee has one set of contact information, and each set of contact information belongs to one employee. This is one-to-one relationship. You could link these tables using a shared primary key such as employee ID to maintain a single detailed record for each employee. This structure ensures that contact information is neatly organized and easily accessible for each employee. So in the mapping one-to-N relationship or one-to-many relationship between the customers and orders, because of the mandatory one in the relationship, we could have modeled ordered as a weak entity and submits as an identifying relationship. In the ER diagram here, we generally don't depict the idea of a foreign key. This is because the only purpose of a foreign key is to implement the relationship. It is not a meaningful piece of the data in itself. Note that any time you have a many-to-many relationship, whether or not it contains its own attribute, it must be implemented as a separate relation table. Often this is called an intersection table or junction table. In this example, the new table's primary key is a composite formed by two foreign keys, one of each entity, comprising many-to-many relationship or M2N relationship. Employee and the course in this case are the good examples. Although one-to-one relationship are less common than one-to-many and many-to-many relationships, they still can occur. The ER diagram shows that a nurse could be in charge of the most one care center, and that each care center must have exactly one nurse in charge. So since the care center must have a charge nurse, this means the foreign key in this relationship goes into care center table. Also, because of the mandatory one in the relationship, this must mean that the nurse in charge field can never have a null value. As we saw earlier in chapter 2, many-to-many relationships can also be modeled as associative entities. Sometimes this is preferable. Associative entities will map onto intersection tables in the resulting logical data design. So the mapping associative entities, let's understand that within a little example that I will illustrate now. In a university setting, students can enroll in multiple courses, and each course can have many students. As we discussed earlier, to map this many-to-many relationship, you would create an associative entity type called enrollments. The enrollments table would have columns like student ID, course ID, which are foreign keys referencing to the students and courses tables, respectively. This table allows you to track which students are enrolled in which courses, along with any additional information about the enrollment, such as the semester or the grade received. In a library system, as discussed earlier, a book can have multiple authors and an author can write multiple books. To manage this many-to-many relationship, you would create an associative entity called book authors. This table would have a column like book ID and author ID, which are foreign keys referencing the books and authors tables. The book authors, which is the conjunctive table, allows you to track which authors wrote which books and can also store additional information such as the order of the authors for a particular book. And as we discussed earlier, the movies database, a movie can belong to multiple genres or genres, and each genre can be associated with many movies. To handle this many-to-many relationship, you would create an associative entity called movie genres. This table would have columns like movie ID and genre ID, which are foreign keys referencing the movies and genre tables. The movie genres table allows you to track which genres each movie belongs to, making it easy to query movies by genre or to find all the genre associated with a particular movie. In each of these examples, the associative entity serves as a bridge between that connects the two main entities, enabling you to effectively manage and query the many-to-many relationships between them. So mapping associative entities involve creating a bridge or junction table to manage many-to-many relationships. This is the summary between two other tables. So here order line, which implements a many-to-many relationship between order and the product, is explicitly modeled as an associative entity. This is a good example in terms of the entity relationship. So examples of mapping an associative entity. This is another example. The resulting intersection table connects orders to products. The same would have been true if there was a many-to-many relationship instead of an associative entity in the ER model. So mapping associative entity to relational database is essentially identical to mapping many-to-many relationships in relational databases. There can only be one order line between a particular product and a particular order. You can't duplicate the same order ID and the same product ID. In this case, the associative entity has its own identifier. So let's look into the next slide. Thus, the foreign keys of the resulting intersection relation are not part of the primary key. So it is possible to have multiple shipments from the same vendor to the same customer. Here, primary key differs from the foreign keys. Mapping unary relationships. Let's look into this in a little bit more depth with few examples. Mapping unary relationships involves creating a relationship within a single table where records can be related to other records within the same table. Let's look at employees and managers example as our first one to understand. In a company's organizational structure, each employee has a manager who is also an employee. To map this unary relationship, you would add a column to the employees table called manager ID, which is a foreign key that references to the employee ID of another record in the same table. This structure allows you to track the hierarchical relationships between employees and managers, making it easy to query the organizational hierarchy, such as finding all employees who report to the specific manager. Another example can be an e-commerce platform with each category can have multiple subcategories, and each subcategory is itself a category in its unique condition. To manage this unary relationship, you would add a column to the categories table called parent category ID, and which is a foreign key that references to the category ID of another record in the same table. This structure enables you to create hierarchical tree of categories and subcategories, permitting for easy navigation and querying of product catalog. So let's take a social network as another example. Each user can be friends with other users. To map this unary relationship, you would create a junction table called friendships with columns like user ID 1 and user ID 2, both which are foreign keys referencing the user tables. This table allows you to track the friend relationships between users, making it easy to query users' list of friends or to find mutual friends between the two users. Additionally, the friendships table can store attributes specific to the friendship, such as the date of the friendship was established. In each of these examples that I just discussed, the unary relationships is mapped by referencing the primary key of the same table either directly or through a junction table. This structure enables you to model hierarchical or network-like relationships within this single entity. So the ER diagram involves a one-to-many relationship that is given on the screen at this moment. Thus, the foreign key is in the same table as the primary key. This is often called recursive key as well, because it points at record in the same table. Because of the optional relationship, it is possible for an employee not to have any supervisor. Therefore, manager ID field could be null. This structure is an example of storing hierarchies. It means the representation of a supervisor who has subordinates, and these subordinates could in turn manage other subordinates, and the list can go on. As always, any many-to-many relationship requires a separate table or relation. Bill of materials is another classic example of representing hierarchies in a database. An item may have sub-items which could in turn have other sub-items. However, there is a difference between this and the employee example from earlier. A given employee can have only one direct manager, but a component that conceivably is a part of the many other items, that is many-to-many relationship. So let's look into mapping ternary or n-ary relationship with few examples. Mapping ternary relationships involves creating a relationship between three different entities. This is less common than binary relationships, but can be necessary in certain complex scenarios. So let's take our first example as suppliers, products, and warehouses. In a supply chain management system, suppliers provide products to various warehouses. To map this ternary relationship, you would create a junction table called supplier product warehouse. That's one word. This table would have columns like supplier ID, product ID, and warehouse ID, which are foreign keys referencing the suppliers, products, and warehouses tables, respectively. This table allows you to track which suppliers provide which products to which warehouses, along with any additional information such as quantity supplied or delivery date. Next would be students, courses, and teachers example. In the educational system, students enroll in courses taught by specific teachers. To manage this ternary relationship, you would create a junction table called student course teacher. That's one word. This table would have columns like student ID, course ID, and teacher ID, which are foreign keys referencing the students, courses, and teachers tables. The student course teacher, one table, allows you to track which students are enrolled in which courses taught by which teachers, making it easy to query enrollment data and manage class rosters. And let's look at the healthcare system as another example. In a healthcare system, doctors schedule appointments with patients. To map this ternary relationship, you would create a junction table called doctor-patient appointment. That's one word. This table would have columns like doctor ID, patient ID, and appointment ID, which are foreign keys referencing the doctors, patients, and appointment tables. The doctor-patient appointment table allows you to track which doctors have appointments with which patients, along with details about the appointments such as data, time, and location. In each of these examples, the ternary relationship is mapped using a junction table that references the primary keys of three different tables. This structure enables you to model complex relationships involving three entities, permitting for comprehensive data management and querying capabilities. So patient treatment, ternary, as I just discussed, a physician has physician ID, physician name, patient has patient ID, patient name. Patient treatment is P treatment date, P treatment time, and P treatment results. And the treatment has treatment code and treatment description. So you can look at all the relations mapping the ternary relationship in this. So this ER diagram shows that given physician can give a particular treatment to a particular patient, and this could happen more than once. There can be four resulting relations. Patient has patient ID, physician has physician ID, treatment has treatment code or treatment ID, for example. Whereas patient treatment can have patient ID, physician ID, and treatment code. What patient treatment date was, what was the time, and what were the results, if any, by the doctor's notes can be entered in that table, patient treatment, for us to reconsider in the future if there is any need to retest or change any prescription for the patient. So let's look at few examples of mapping supertype and subtype relationships. Mapping supertype subtype relationships involves creating a structure when a general entity supertype is further categorized into more specific entities or subtypes. Let's look at few examples. Let's take employees and their roles as our first example. In a company or an organization, all employees share common attributes like employee ID, name and contact information. However, different types of employees, such as managers, engineers, and salespeople, have additional attributes specific to their roles. To map this type or to map this supertype subtype relationship, you would create an employee table as a supertype. The common attributes are given in the supertype. Then you would create a separate table for managers, engineers, and salespeople as subtypes, each with a foreign key referencing to the employee table and additional attributes relevant to their roles. The next example can be vehicles and their types. In a vehicle registration system, all vehicles share common attributes like vehicle ID, make, model, and a year. However, different types of vehicles, such as cars, trucks, and motorcycles, have additional attributes specific to their types. To manage this, you would create a vehicle table as the supertype with common attributes. Then, you would create separate tables for cars, trucks, and motorcycles as subtypes, each with a foreign key referencing the vehicles table and additional attributes relevant to their types. Next is products and their categories. In an e-commerce platform, all products share common attributes like product ID, name, price, and description. However, different categories of products such as electronics, clothing, and books have additional attributes specific to their categories. To handle this, you would create a products table as a supertype with common attributes. Then you would create separate tables for electronics, clothing, and books as subtypes, each with a foreign key referencing the product table and additional attributes relevant to the categories. Next, we can look at animals and their species. In wildlife database, all animals share common attributes like animal ID, name, and habitat. However, different species of animals such as mammals, birds, and reptiles have additional attributes specific to their species. To map this, you would create an animals table as a supertype and with the common attributes. Then you would create a separate table for mammals, birds, and reptiles as subtypes, each with a foreign key referencing the animals table and animals attribute relevant to their species. Last not the least, users and their roles in a given system. In a software application, all users share common attributes like user ID, username, and email. However, different types of users, such as administrators, regular users, and guests, have additional attributes specific to their roles. To manage this, you would create a users table as a supertype with common attributes. Then you would create separate tables for administrators, regular users, and guests as subtypes, each with a foreign key referencing the users table and additional attributes relevant to their roles. In each of these examples, the supertype table contains common attributes shared by all entities, while the subtype tables contain additional attributes specific to each category or role. The structure allows for efficient data management and querying, as well as the ability to easily extend the system with the new subtypes if needed. So supertype, subtype relationships are essentially one-to-one relationships. So the rules that apply to these mappings will be similar to the rules we applied other one-to-one relationship mapping, as we will see in the next slide. The primary key of the subtype relation table is also a foreign key to the supertype relation. Note that we have not seen this before. We have seen composite primary keys where the part of the primary key is a foreign key, but have not seen a case where the entire primary key is also a foreign key. Therefore, if you ever see a database table where the entity entire primary key is also a foreign key, this should imply that there is a supertype subtype relationship involved. Like these are implemented as one-to-one relationships between employee, consultant, salaried employee, and hourly employee. What is data normalization? Let's look into this in a little bit more depth. The previous slide showed how to map an ER model to a relational database design. If you follow these mappings, then your result will be a well-structured database. But if you just start by creating tables without considering the ER rules or entity relationship rules, then you will likely to get a database that is not well structured. These databases could cause anomalies because of data duplication. In the next several slides, we will see how to correct these anomalies through process called normalization. Let's look into a few normalization examples. Let's take customer orders to understand what data normalization is. In a customer order system, you might initially have a single table that includes order details, customer information, and product information. This can lead to redundancy, especially if the same customer places multiple orders. To normalize this data, you would create a separate table for customers, orders, and products. The customer table would store unique customer information like name and address. The order table would store order-specific details like order ID, customer ID, and product ID and the quantity. The product table would store information about each product. This separation reduces the redundancy and ensures that each piece of data is stored only once. Same example can be applied on the student courses. In a student course enrollment system, you might start with a single table that includes student names, course name, and instructor name. This setup can lead to redundancy if the same student enrolls in multiple courses or if the same instructor teaches multiple courses. To normalize this data, you would create separate tables for students, courses, and instructors and enrollments. The student table would store unique student information. The courses table would store course detail, including the instructor. The instructor table would store unique instructor information. The enrollments table would link students to the courses that are enrolled in. The structure eliminates redundancy and makes the data more manageable. As we are continuing the discussion in terms of the library system, so book and authors can be a good example. In a library system, you might initially have a single table that includes book title, author name, author birth date, and the topic that books is written on. This can lead to redundancy if the same author has written multiple books. To normalize this data, you would create separate tables of books, authors, and topics. The books table would store unique book information. The author table would store author detail like name and birth date. The topics table would store the topic information. You might also have junction table to manage many-to-many relationships between books and authors, as well as books and types or topics. It can be fiction, non-fiction. This separation course ensures that each piece of the data is stored only once and reduces redundancy. If we look at the project management example, in an employee project management system, you might start with a single table that includes employees' names, project names, and project details. This can lead to redundancy if the same employee is involved in multiple projects or if the same project has multiple employees. To normalize this data, you would create separate tables for employees, projects, and project assignments. The employees table would store unique employee information. The projects table would store project details. The project assignments table would link employees to the projects that they are working on. This structure eliminates redundancy and makes it easier to manage the query of the data. The structure can also be called a data store, and that's where the columns and rows reside within a table. Another example can be product categories. In an e-commerce system like Pine Valley Furniture, you might initially have a single table that includes product names, categories, and prices. This can lead to redundancy. If the same category is used for multiple products. To normalize this data, you would create separate tables for products and categories. The product table would store unique product information like names and price. The categories table would store category details. You might also have a junction table to manage the many-to-many relationship between products and categories. The separation reduces redundancy and ensures that each piece of data is stored only once, making the data more efficient to manage and query. Hopefully, this is a good way to learn what data normalization looks. So there are well-structured relations that contain minimal data redundancy and allow users to insert, delete, and update rows without causing data inconsistencies. A general rule of thumb: a table should not pertain to more than one entity type. So goal is to avoid anomalies. Insertion anomaly: adding new rows forces a user to create duplicate data. Deletion anomaly is deleting rows may cause a loss of data that would be needed for other future rows. And modification anomaly is changing data in a row forces changes to other rows because of the duplication. So let's look into this in a little bit more depth. So this is an employee 2 example with 100, 100, 140, 110, 110, 190, 150. So you can see Margaret Simpson has been given twice. Marketing salary is this, the course title taken SPSS, and also course title surveys. And the dates are given. Question: is this a relation? Answer: yes. Unique rows and no multi-valued attributes. The another question: what is the primary key? Answer is composite, employee ID and course title. So let's this is a relation, but it is not well structured relation. This can be an Excel sheet, a worksheet. So insertion, deletion, modification. Insertion cannot enter a new employee without having the employee take a class or at least empty fields of the class information. Deletion: if we remove employee 140, we lose information about the existence of a tax accounting class. Modification: giving a salary increase of employee 100 forces us to update multiple records. Why do these anomalies exist? Because there are two themes, entity types. In this one relation, there are employees and there are courses. This results in data duplication and an unnecessary dependency between the entities. So steps in the normalization. It is important that the database reach their third normal form, Boyce code, BOYCE -CODD. Fourth and fifth are theoretical interest, but not generally considered vital for qualifying as a set of well-structured relation. So let's look into the Boyce code fourth and fifth later, but let's look into third normal form with few examples, and then you will understand why the third normal form is significantly important. The third normal form, or 3NF, is a stage in the normalization process that builds upon the first normal form, second normal form, And in third normal form, the goal is to eliminate transitive dependencies, meaning the non-key attributes are dependent only on the primary key. Let us look at three examples to understand all this: removal of multi-valued attributes, removal of partial dependencies, removal of transitive dependencies to achieve the third normal form. The first example we'll take as customer orders, as we are discussing Pine Valley in depth. In a customer order system, you might have initially normalized data into separate tables for customers, orders, and products. To achieve third normal form, you ensure that all non-key attributes are dependent only on the primary key. The customer table would include unique customer information like customer ID, name, and address. The orders table would include order specific details like order ID, customer ID, and product ID and quantity. The products table would include product information like product ID, product name, and product price. In this setup, each table is designed so that non-key attributes like customer address or product price are dependent only on the primary key customer ID and product ID, ensuring that the data is in third normal form. The student courses. In a student course enrollment system, you might have separate tables for students, courses, instructors, and enrollments. To achieve third normal form, you ensure the non-key attributes of the dependent only on the primary key. The students table would include unique student information like student ID, name, and contact details. To ensure table would include course details like course ID, name, and instructor ID. The instructors table would include unique instructor information like instructor ID, name, and department. The enrollment table would link students to the courses that they are enrolled in using the student ID and course ID. In this structure, non-key attributes like student name or instructor department are dependent only on the primary key, ensuring that the table is in third normal form. Again, let's go to the library. In the library system, you might have separate tables for books, authors, and topics like fiction or non-fiction, along with junction tables to manage many-to-many relationships. To achieve third normal form, you ensure that all non-key attributes are dependent only on the primary key. The books table would include unique books information like book ID, title, and publication date. Authors table would include author detail like author ID, name, and the birth date. The topic table would include topic information like topics, topic ID, and topic name, fiction or non-fiction. Junction tables would manage the relationship between books and authors as well as books and topics. In this setup, non-key attributes like author name or topic are dependent only on the primary keys, ensuring that the data is in third normal form. In each of these examples, the data is structured so that non-key attributes are dependent only on the primary key, eliminating transitive dependencies and achieving the third normal form. This ensures that the data is organized efficiently and reduces redundancy. So let's look into functional dependencies and the keys with few examples. Functional dependencies are a critical concept in database normalization, including the third normal form. A functional dependency exists when the value of one attribute or set of attributes uniquely determines the value of another attribute. In the context of third normal form, the goal is to eliminate transitive dependencies, which occur when a non-key attribute is dependent on another non-key attribute rather than directly on the primary key. For example, in a customer order system, if the customer's address is dependent on the customer ID and the order details are dependent on the order ID, there should be no indirect dependencies where order details dependent on the customer's address. By ensuring that all non-key attributes are functionally dependent only on one primary key, the data is organized efficiently and the redundancy is minimized. Whereas the keys play a crucial role in achieving the third normal form. The primary key is a unique identifier for each record in a table, and it is used to enforce entity integrity. In third normal form, all non-key attributes must be fully functionally dependent on the primary key, meaning that the primary key uniquely determines the values of these attributes. Additionally, there should be no partial dependencies where a non-key attribute is dependent on only one part of the composite primary key. For example, in a student course enrollment system, the primary key for the enrollments table might be a composite key consisting of student ID and course ID. Each non-key attribute, such as the enrollment data, should be dependent on the entire primary key, both student ID and the course ID, not just one part of it. By ensuring that all non-key attributes are dependent only on the primary key and the data is structured in a way that eliminates redundancy and maintains data integrity. So the first normal form is no multi-valued attributes. For every attribute values is atomic. And the figure 425 mentioned earlier is not in first normal form multi-valued attribute. It is not a relation. Whereas figure 426 is in first normal form, all relations are in the first normal form. There you go. This table has with multi-valued attributes not in first normal form. This is not a relation. Whereas this is a relation, but not a well-structured one. So the anomalies in this relation, if insertion, deletion, and update, if new products is ordered for order 1007 of existing customer data must be re-entered, causing duplication, like Microsoft Excel sheet. Why do these anomalies exist? Because there are multiple themes, entity type in one relation, and the results in this results in duplication and unnecessary dependency between the entities. In case of deletion, if we delete the dining table from order 1006, we lose information concerning the item's finish and price. Update, changing the price of product ID 4 requires update in multiple records. Second normal form. First normal form plus every non-key attribute is fully functionally dependent on the entire primary key. Every non-key attribute must be defined by the entire key, not only part of the key. No partial functional dependencies in second normal form. So this is the example. Functional dependency diagram for an invoice. The full dependencies between order ID, product ID, and the ordered quantity. The partial dependencies are order date, customer ID, customer name, and customer address. Another partial dependencies are product description, product finish, and product standard price. So therefore not in a second normal form. However, this is the second normal form where we remove the partial dependencies like order ID, product ID has order quantity, order line is a third normal form. Product ID, product description, product finish, product standard price, whereas the product is a third normal form. So you can look at the customer order, getting it into the second normal form. That allows us to go to the third normal form. Partial dependencies are removed, but there are still transitive dependencies in this pictorial representation is available. So we have these separate relations. There is no partial dependency, but still have several transitive dependencies. We'll fix this in next splitting customers from orders. So the third normal form, as I discussed in quite detail, the two normal form plus no transitive dependencies or functional dependencies on non-primary key attributes. Note that this is called transitive because the primary key is a determinant for another attribute, which in turn is a determinant of a third. The solution is non-key determinant with transitive dependencies go into a new table. Non-key determinant becomes primary key in the new table and stays as a foreign key in the next level of normal form. So removing transitive dependencies, order ID, order date, and customer ID, and the customer table has customer ID, customer name, and customer address, getting into third normal form. The transitive dependencies are removed here. So the relational schema for invoice data, Microsoft Visio notation, the customer places an order, order includes order line has order ID, product ID, and ordered quantity, and order line is the product is ordered in the order line that actually in the end of the day customer receive. If we had started with a thorough entity relationship model, we would not have wound up with one big table containing multiple themes. So we should not have wound up in that. The original table basically had three separate entities all wrapped into single relation customer, product, and order. Furthermore, it hid the fact of a many to many relationship between orders and the products. This illustrates the danger of going straight into logical database design without first performing the conceptual model analysis, but this sort of thing happens all too often. Merging relations. So, view integration, combining entities from multiple ER models into common relations. Issues to watch out for when merging entities from different ER models. They have synonyms, homonyms, transitive dependencies, supertype, subtype relations. I would suggest you to read this in the database, in the actual book that is prescribed in this lecture and is on the given on the first slide to know more about this in depth. So enterprise keys are primary keys that are unique in the whole database, not just within the single relation. This corresponds to the concept of an object ID in object-oriented system. So the copyright is this work is protected by United States copyright laws. I would suggest you not to disseminate this work. Just keep it with you for your learning, and you are most welcome to read the book uh, in relation to the first normal form, second normal form, and third normal form, because that'll give you a huge idea that how databases are helpful for us to understand individual attributes and fields which can take data uh, and add data for us to get a record and check the history of a customer who had placed orders and bought some sort of furniture. It can be bedroom furniture, it can be dining room furniture, it can be drawing room furniture, or it can be a library furniture that they ordered for their home. Happy learning. See you in the next lecture, and let's continue.